Assalamu alaikum students. I hope you are good and doing well. In this video we will study how to derive the R square in simple linear regression. Before deriving it, we first need to know what R square is. So R square basically is the coefficient of determination. It is a measure of goodness of fit. It tells us how best or how good our sample regression function fits the data. Remember that we are talking only about the sample regression line or sample regression function, how much or how well it fits the data. The better the fit, the higher the R square, and first the fit, lower the R square. In other words, R square tells us how well our included x variables explain the dependent variable. How much variation in y is explained by our included x variables. So this is the R square. So next we study the properties of R square. Remember that R square is always lies between 0 and 1. If R square equal to 1, it means that there is perfect fit and all the observations lie exactly on the sample regression line. But if R square is 0, this means that none of the variation in y is explained by our x variables. The closer the R square to 1, the better the fit, and closer the R square to 0, worst the fit. It means that our model is poor. Our independent variables does not explain the dependent variable. So we need to review our independent variables included in the model. Second property, that R scale is always the non-negative function of the additional x variables. It means that if we increase the x variables in the model, the R square will always increase, even though the additional variable may not be the good predictor of y. So third property is that in simple linear regression, R square is always equal to the square of correlation coefficient between x and y. If we find the correlation coefficient given by the R, then if we square it, we get the coefficient of determination. Look at this formula of R, the correlation coefficient between x and y, which is equal to the covariance between x, y divided by the standard deviation of x multiplied by standard deviation of y. So this is the formula of coefficient of correlation between x and y. If we square this, we will get the coefficient of determination, which always lies between 0 and 1. This holds true only for the simple linear regression, but not for the multiple linear regression. Now consider these two scatter plots I have drawn, case A and case B. You can see that in case A, the observations, the dots, are closely tied to the sample regression function. So for this scatter plot, R square would be high. How much we cannot exactly tell unless we know the formula of R square. I will discuss it soon. If we see the diagram B, here the observations are scattered more around the sample regression line. For this scatter, R square would be low. So if observations are closely tied to the sample regression function, it means that our x variable provides us a good fit of the actual y. But if observations are scattered widely around the sample regression function, it means that our included variables are not a good predictor of y. Now let's understand R square through the Venn diagram. Here are the Venn diagram. Each circle shows the variation in each variable. For example, this circle shows the variation in y and this circle shows the variation in x variable. The overlap between them shows how much R square is. So since there is no overlap between x and y, so R square would be 0. It means that none of the variation in y is explained by x. Now consider this diagram, which is case B. Here y and x are overlapping. The two circles are overlapping but very little. So the R square would be very close to 1. The R square would be very close to 0. Maybe 0.1, 0.2, 0.3, but it would be low because the overlap between y and x is very small. The greater the overlap, the greater the R square is. The greater is overlap, it means greater variation in y is explained by x. Lower the overlap, lower the variation in y is explained by x. Consider this example where the overlap is much greater as compared to case B. Here, as compared to case B, more of the variation in y is explained by x because overlap is much greater as compared to case B. So here R square may be 0.4, 0.6, 0.5. Now consider this case D. Here the overlap is much greater as compared to case B or C. It means that more of the variation in y is explained by our x variable, so R square would be close to 1, maybe 0.9, 0.8. And look at the case E. Here the two circles are overlapping exactly. You cannot see, but two circles y and x are overlapping with each other, therefore R square is equal to 1. So it means that all the variation in y is explained by our x variable. So there is no unexplained variation. So there is perfect fit and all the observations would lie exactly on the sample regression line, which is rare case in practice. I talked about R square, that it is the total variation in y that is explained by our x variables. So how many types of variation in the regression model? So there are three types of variation in the regression model. First, it is the total variation in y. It is the scattered of y values around the mean of y. Simply, total variation in y is the spread of y values around its mean. Explained variation, this is the variation that is explained by our independent variable. And unexplained variation, it is a variation that our model fails to explain. Total variation is also called total sum of squares, which is equal to explained sum of square due to our x variables, and residual sum of square due to our error term or due to residual or due to unobserved factors. Total sum of square can be written as sum of yi minus y hat squared. So total sum of square is the sum of square deviation from mean. Similarly, explained sum of square equal to sum of y hat minus y bar square. It is a variation in y hat around its mean. Since we studied that in the numerical properties of sample regression line, that y bar is equal to y hat bar. It means that the mean value of estimated y equal to the mean value of actual y. So y bar and y hat bar are equal. So this is a variation in y due to x. For example, if total sum of square is 100 and explained sum of square is 60, it means 60% of the variation in y is explained by our x variable, while 40% is unexplained. It is due to residuals. Residual sum of square is the difference between sum of yi minus y hat squared. So it is a variation in y that is unexplained. This variation is not explained by our model. So if this variation is not explained by our model, then who explains this variation? So this variation comes from the unobserved factors. These are the omitted factors from the model, which we cannot observe, or even we can observe, we cannot measure them. So now let's see the formula of r square, the coefficient of determination. R square equals explained variation due to x variables divided by total variation in y. So this is the general formula which can also be used in the multiple linear regression. In other words, r square can be written as explained sum of square divided by total sum of squares, which is equal to these ratios: sum of y hat minus y bar squared and sum of y minus y bar squared. I denote these differences with small y hat and this difference with small y. This small y shows the deviation of y around the mean, and small y hat shows the deviation of y hat from its mean. So let's understand these variations through a diagram. This is the mean value of y, and this is the actual value of y. The difference between the actual value and mean value of y is known as total sum of square. So this is the total variation in y. I told total variation means spread of y around its mean. So this is the spread of y around the mean. Next, this is y hat. The difference between y hat and y bar is known as explained sum of square. This variation is explained by our model, this variation, but this variation y minus y hat is unexplained. This is known as residual sum of square. This variation is due to our unobserved factors. So if we add the explained sum of square and residual sum of square, we will get the total sum of square. So total variation is equal to explained variation, that is y hat minus y bar, and unexplained variation, that is y minus y hat. So TSS is equal to ESS plus RSS. If we divide the whole equation by TSS, we would get this equation: 1 equal to R square plus RSS over TSS. Divide TSS by TSS, ESS by TSS, and RSS by TSS, we will get this equation. So R square can also be written as R square equal to 1 minus RSS over TSS, which is the formula 2. This is formula 1 to calculate R square. This is formula 2, 1 minus RSS over TSS.